what if? Just two simple words, but they really, they drive everything, don't they? Pushing us right to the edge. Today, we're taking a deep dive, looking at some pretty huge cosmic what-ifs. These are thought experiments, but, grounded in actual physics.
That's right. We've got two really distinct scenarios lined up from the sources. First, there's this hunt for, well, a single missing particle, one that might just complete our picture of reality.
Yeah.
And second, what if our sun, the star that gives us life, suddenly turned into, well, the universe's most violent kind of bomb?
Wow. Okay. Cosmic order versus raw power. Let's unpack that first one. So for 50 years, the standard model of particle physics, that's been our best guide, right? Our kind of cosmic recipe book for the small stuff.
Incredibly successful, yeah. It explains three big forces: electromagnetism, the strong force, the weak force perfectly.
Wow.
With their particles like photons, gluons, It all works beautifully.
But there's a gap, a big one.
Exactly. The most familiar force, gravity, the thing holding you down right now, it's just not in the model. It's the ghost at the feast, like you said.
And the particle for gravity, if it exists, that's the graviton?
Graviton, yes. And theory says it'd be, well, practically a ghost, massless light speed.
But incredibly weak interaction.
Almost immeasurably weak. Think about this. A tiny fridge magnet. It can pick up a paperclip against the entire gravitational pull of Earth.
Huh. Never thought of it like that.
That's the scale difference. Gravity is like 10 times weaker than electromagnetism down at that tiny level. So yeah, detecting one graviton directly, you'd need a detector maybe the size of a galaxy.
Okay, hold on. A galaxy-sized detector. That's obviously not happening. Sounds like something out of sci-fi. So how do we even begin to look for this thing? There must be a cleverer way, right?
Right. Forget big, think quantum. There's this pretty radical idea, a cosmic trap. Imagine a big cylinder of something like superfluid helium, super still, super cold, cooled right down to its quantum ground state. Perfectly quiet, quantumly speaking. Then you wait. You wait for something huge, like two neutron stars crashing together way out there.
And LIGO would see the gravitational waves from that.
Exactly. LIGO gives us the heads up, the trigger. As that wave, which is just tons of gravitons, washes past, maybe one single graviton gets absorbed by our super cold resonator.
And that one interaction, it makes the resonator do something.
It forces a tiny quantum jump, a single quantum ding. They call it the gravitophononic effect. The quietest sound possible, really.
Wow. Okay, so this tiny ding, that sounds small, but you're saying this is huge. This shakes physics. How?
Because for 100 years, we've had these two amazing theories. Einstein's general relativity for big stuff, stars and galaxies, quantum mechanics for the tiny stuff, atoms and particles. They both work incredibly well in their own areas.
So they don't play nice together.
Not at all. They fundamentally contradict each other. They break down completely in places like the center of a black hole or the Big Bang itself. The graviton could be the bridge, the translator between them.
So finding it proves gravity is quantum.
It'd be the first direct proof, yes. The first real step towards that theory of everything physicists dream about. It might even, hint at extra dimensions of space hidden away. It really changes everything about how we see reality.
Okay, from that incredibly subtle hunt, let's flip to the other extreme. Raw, cosmic violence. What if our sun exploded? But first, let's be clear. Our sun won't go supernova, right?
Absolutely not. It's just not massive enough. You need a star maybe 8-10 times heavier than our sun for that kind of fireworks.
So what is our sun's actual endgame then? Less bang, more whimper.
Hey, well, still pretty dramatic. It'll swell up into a red giant first. Big enough to swallow Mercury, Venus, probably scorch Earth completely. Then its outer layers just sort of puff off into space, creating this beautiful thing called a planetary nebula. And what's left behind is a tiny, incredibly dense core, a white dwarf, just an ember cooling down forever.
Okay, so our sun gets a pass. But let's run the hypothetical. What if it was one of those massive stars? What actually happens inside to trigger a supernova?
It's all about fusion and gravity. Massive stars fuse elements way faster than our sun. Hydrogen to helium, then helium to carbon, oxygen, neon, silicon. It gets faster and faster. Carbon might burn for thousands of years, but silicon, maybe just for a few days. Yeah, until it hits the end of the line. Iron. Fusing iron doesn't release energy, it consumes it. So the outward pressure holding the star up just vanishes instantly. Gravity wins, catastrophically.
And that's when you get what the sources call the universe's most violent second.
Pretty much, yeah. The core, maybe the size of Earth, but heavier than our sun, collapses inwards. In less than a quarter of a second, It shrinks down to the size of a city, hitting speeds like 70,000 kilometers per second.
Unbelievable speed.
It slams into itself, forming this incredibly dense ball of neutrons and the material still falling in. It bounces off this neutron core. That creates a huge shock wave moving outwards, but it often needs a boost.
A boost from what?
Neutrinos. An absolutely unimaginable flood of neutrinos streams out from the collapsing core, and they dump energy into that shockwave. That's what really blows the star apart. And in that explosion, all the heavier elements, gold, platinum, uranium, the stuff we find on Earth, get forged and blasted out into space.
That process is just mind-bending. But bring it closer to home. Imagine that happening to our sun just, 8 light minutes away.
Okay, well, for 8 minutes and 20 seconds, we wouldn't know a thing. Sunlight is normal. Then the neutrinos hit. Silently. But they'd pass through everything, irradiating the entire planet from the inside out, cooking us instantly, lethally.
Right.
Seconds later, the light and radiation arrive, blindingly bright. It would vaporize the side of Earth facing the sun, strip away the atmosphere, boil the oceans, melt rock.
And the rest of the planet.
The shockwave from the blast itself would arrive a bit later, but honestly, after the radiation, what's left of Earth? Just a charred, maybe broken cinder, flung out into the cold darkness of interstellar space. A dead, rogue planet.
Wow. Okay. So from hunting a nearly undetectable particle, a key to the universe's rules, to the sheer, terrifying, creative power of a star tearing itself apart, it really shows you the two sides of the cosmos, doesn't it?
It really does.
Yeah.
The intricate hidden laws on one hand and this unbelievable raw power on the other. And it just goes to show how asking what if, even about things that seem impossible, lets us grasp a bit more of that reality, even as, fragile beings on this one small world.
It definitely broadens the perspective. It makes you wonder, doesn't it? What other cosmic what ifs are out there? Just waiting for us to ask the right question, maybe revealing whole new chapters about our universe.